predicting perceptual decisions using visual cortical, population responses and choice history. Our understanding of the neural basis of perceptual decision-making has been built in part on relating co-fluctuations of single neuron responses to perceptual decisions on a trial-by-trial basis. The strength of this relationship is often compared across neurons or brain areas, recorded in different sessions, animals, or variants of ATASC. We sought to extend our understanding of perceptual decision-making in 3 ways. First, we measured neuronal activity simultaneously in early, primary visual cortex, V1, and mid-level, V4, visual cortex while macaque monkeys performed a fine orientation discrimination perceptual task. This allowed a direct comparison of choice signals in these 2 areas, including their dynamics. Second, we asked how our ability to predict animals' decisions would be improved by considering small simultaneously recorded neuronal populations rather than individual units. Finally, we asked whether predictions would be improved by taking into account the animal's choice and reward histories, which can strongly influence decision-making. We found that responses of individual V4 neurons were weakly predictive of decisions, but only in a brief epoch between stimulus offset and the indication of choice. In V1, few neurons showed significant decision-related activity. Analysis of neuronal population responses revealed robust choice-related information in V4 and substantially weaker signals in V1. Including choice and reward history inform a tie-on improved performance further, particularly when the recorded populations contained little decision-related information. Our work shows the power of using neuronal populations and decision history when relating neuronal responses to the perceptual decisions they are thought to underlie. Decades of research has provided a rich description of how visual information is represented in the visual cortex. Yet how cortical responses relate to visual perception remains poorly understood. Here we relate fluctuations in small neuronal population responses, recorded simultaneously in primary visual cortex, V1, and area V4 of monkeys, to perceptual reports in an orientation discrimination task. Choice-related signals were robust in V4, particularly late in the behavioral trial, but not in V1. Models that include both neuronal responses and choice history information were able to predict a substantial portion of decisions. Our work shows the power of integrating information across neurons and including decision history in relating neuronal responses to perceptual decisions. One way to understand how the activity of sensory neurons contributes to perception is to measure neuronal responses and perceptual reports simultaneously, and assess their covariation. This approach has revealed that trial-to-trial fluctuations in individual visual cortical neurons are weakly predictive of animals' choices in a perceptual task. Such neuron choice correlations have been observed in many cortical areas. Theory suggests that the pattern of neuron choice correlations can be used to infer how sensory representations are read out to reach perceptual decisions. Although inactivation experiments have shown that neuron choice correlations do not indicate that a neuron, or rather, the area in which it resides, is necessary for behavior, correlative approaches remain an important ingredient for understanding perceptual decision-making and for interpreting the consequences of causal perturbations. To date, much of our progress in understanding neuron choice correlations has relied on a stereotyped experimental AP approach, isolating individual neurons in an area of interest, tailoring the task in each session to the functional properties of the recorded neuron, and relating neuronal responses to perceptual reports using choice probability analysis. This approach has several limitations, which we sought to overcome in the current study. First, tailoring the task, example, direction of motion in a motion discrimination task, to each recorded neuron complicates the comparison of choice signals across cells. Comparisons of choice signals in different brain areas are even more problematic, because these are often measured in different sessions, animals, or even tasks. Behavioral strategies can vary strongly across similar tasks and even across animals performing identical tasks, and these variations in strategy likely influence choice information. Allow a direct comparison of choice signals in early and mid-level primate visual cortex. We therefore simultaneously recorded neurons with overlapping spatial receptive fields, RFs, in primary visual cortex, V1, and area V4 while monkeys performed a fine orientation discriminator tie-on task. The task was not adjusted to the functional properties of the sampled neurons, except for placing the behavioral stimuli in the aggregate spatial RF. Second, with few exceptions, neuronal correlates of perceptual decisions have been studied in single neurons, although sensory information is encoded by neuronal populations. Here we record simultaneously from small neuronal populations, up to 30 neurons, in V1 and V4 and read out their responses to predict choice. We compare the view they provide about choice representation to that afforded by single neurons. Finally, perceptual decisions are influenced not only by sensory evidence, but also by a host of other factors, including the history of choices and rewards. These history effects are well documented in humans and other animals but rarely considered when relating neuronal responses to choices. We assess how consideration of choice history information improves our ability to predict choices on the current trial using neuronal responses, and whether the choice information available in neuronal responses directly reflects choice history. Subjects. We used 2 male, adult cynomolgus macaques, Macaca fascicularis. All procedures were approved by the Institutional Animal Care and Use Committee of the Albert Einstein College of Medicine and were in compliance with the guidelines set forth in the National Institutes of Health Guide for the Care and Use of Laboratory Animals. Animals were first familiarized with a restraining chair, CRIST instruments, and then implanted with a titanium head post. Implantation was performed under isoflurane anesthesia, following strict sterile procedures. A postoperative analgesic, buprenorphine or flunixin, an antibiotic, enrofloxacin, were provided. Animals recovered for at least 6 weeks before the initiation of behavioral training. Task and behavior. Animals viewed a calibrated monitor, EMAMA, 1024-768 resolution, 100 Hz refresh, from a distance of 57 centimeters. Visual stimuli were generated using custom OpenGL software, which also controlled task contingencies. Eye position was monitored using a video eye tracking system, SR Research, with a sampling rate of 1 kHz. Animals were positively reinforced with a drop of liquid reward. Animals performed a 2 alternative force choice orientation discrimination task. Trials began with subjects fixating a bright spot, 0.15 degrees to 80 candelas per square meter, on a gray background, 40 candelas per square meter. After 0.2s, we presented a drifting, sinusoidal grating in the parafoveal visual field. For 0.2s, gratings were presented at full contrast, with a drift rate of 6 Hz and spatial frequency of 2. For CPD, 0 degrees gratings drifted downward, 90 degrees gratings rightward. 0.2s after stimulus offset, the fixation spot was replaced with 2 targets on the vertical meridian, eccentricity of 2.4, 5.6 degrees. The animal reported its choice by making a saccade to one of the targets. All orientations that were closer to vertical than 45 degrees were associated with the top target. Orientations closer to horizontal than 45 degrees were associated with the bottom target. The range of orientations was adjusted for each animal to span perceptual threshold, and included the perceptually ambiguous stimulus, 45 degrees, which was rewarded randomly. In most sessions, the probability of presenting a 45 degrees orientation was twice that of the other orientations. Reward was doubled after 3 consecutive correct responses. Reward was reset to its base volume after an incorrect response. The inter-trial interval was 2s, but was extended following an erroneous choice. Eye position had to stay within a 1.4 degrees window until the appearance of the targets, else the trial was aborted and discarded. We measured the animal's performance by fitting a cumulative Gaussian function to the psychometric function, using maximum likelihood for a Bernoulli process. We defined the bias as the difference between the mean of the Gaussian and 45 degrees, and the threshold as the Gaussian SD, equivalent to the point where the animal chooses a correct answer in 84% of the trials. Only sessions that had a threshold 6 degrees and a bias 3 degrees were considered further. 82% of the available sessions exceeded these criteria. Recording. Training continued until the subjects reached asymptotic performance, after which we implanted microelectrode arrays, black rock systems, in V1 and V4. We targeted the arrays to matching retinotopic locations, relying on anatomical markers and previous mapping studies. Microelectrode